I'd like to talk about the relationship between thermodynamics and kinetics when reading a phase diagram. Phase diagrams are purely thermodynamic constructs, and the phase diagram is basically a map telling you at a given composition, at a given temperature, if you make a system, you let it sit infinitely long so it comes to equilibrium, what phases will be present, what will be the composition of the phases. It tells us nothing about kinetics. And I want to point out that we can use these phase diagrams to talk about non-equilibrium structures, and the quantification of how to do this is a little bit more complicated than we're going to talk about in this class, but I want you to see the basic thinking behind how to do this. So let's make a simple phase diagram. Again, an A-B binary phase diagram. So A on the left, B on the right, XB, and this is going to be the temperature on the y-axis. So let's make the simplest phase diagram we can make, just one of these lenses with liquid, alpha, and alpha plus liquid. So thermodynamically, at any point, we're talking about equilibrium. So for example, if I start out at this composition, at this point, and I cool down, the composition of alpha phase at that point is given by that X, B, alpha. I'm just going to call this alpha hot because it's at high temperature. If I cool it down a little bit more, I have X, B, alpha, mid. And as I cool it down almost to the point of crossing, well, we actually get composition, which is X, B, alpha, low for low temperature. And that's exactly the same, or very, very close to the same, as our overall system XB star. If we think about this in terms of thermodynamics, at this point, I have a system which is liquid with little crystals of alpha. And those alphas, we have this composition. In the middle range, I have liquid, and I have bigger chunks of alpha that have formed. Maybe some of these have touched each other a little bit. Alpha, alpha, alpha. And, at this point here, it looks like it's about maybe 60% alpha. I should drop some more in there, huh? Alpha. And the composition is different. But in equilibrium, all of these have exactly the same composition. And then lastly, at this point, we'll have something like this. And we might have a little bit of liquid kind of in the phase boundaries here. But it's almost all alpha, and it has this composition, XB low or XB star. That's an equilibrium. If instead you imagine we cool it down relatively quickly, well, what happens is that alpha, which is very rich in A atoms, in the solid, they don't have time to diffuse outward and get absorbed into the liquid, right? Because we know that as we cool down, our alpha loses A atoms And what actually happens is we wind up with a solid that has a different composition on the interior as it has the exterior. So for example, if let's say green is my non-equilibrium structure, I'll have alpha, and I'm going to use a green to mean my A atoms. As I cool down further, that alpha stays. A way to think of this is you can think of it as the liquid being pushed to the B rich because the A is being trapped in the solid. And the next liquid to form a solid comes here, ejects. So you can think of it all along here as this being a kind of a series of steps. I mean, they're infinitesimally small, but a series of steps nonetheless as solid forms. And at the end of the day, what you're going to wind up with grains that in the interior, you have A rich, and the exterior regions, right in here, it's going to be A poor. And this phenomena is called coring. And it's a consequence of kinetics. Most of the time, for example, in your classes here, we're not going to be asking you about this. We're going to be talking about equilibrium. For example, when I teach 201, I don't want people to quantify this because quantifying that is actually very difficult. Understanding the effect of cooling rate on the solubility of A atoms and the diffusion outwards. It depends very strongly on the material class, the rate of diffusion, the cooling rate, and even the phase fractions, and also the rate of diffusion in the liquid. So it's complicated, but as materials engineers, what we want to do is we want to use this equilibrium thermodynamic information, which we can get this either from measurements or from calculations, and we want to figure out how to create non-equilibrium structures by using kinetics, by changing the rate of cooling, by changing the local geometries, by changing the pressure. So this is what happens when you go beyond thermodynamics and you think about kinetic effects as well.